Hello everyone. In the previous video I explained the proportional controller, and in this video today I'm gonna explain the integral controller, and also I'm gonna explain another controller called PI controller. From the previous videos we know that the proportional controller cannot eliminate the steady state error, and this is why we need the integral controller. Okay, so let's start simulating the integral controller. As we explained in the proportional controller, we need a step input, then we need summation point, next we need gain, because the integral controller also has a parameter here called ki, so we need a block that represents this gain value, and then we need a transfer function. This transfer function for the integral controller, and then we need another transfer function for the process. So do you know what is the transfer function of the integral? If you studied the integral controller, you will know that the integration in time domain converts to 1 over s in s domain. So we are gonna here write 1 over s. So put this 0 and click OK. Then we need to connect all of these items. Don't forget to convert the feedback to negative. Then we need oscilloscope. We make it with 2 parts to connect the input and the output. Okay, so after connecting all the blocks in our project, let's start simulating the project. Okay, double click here, and here is the output and the input of our system. From the figure you can notice the following. First, the output is going to be equal to the input at the steady state, and this indicates that the steady state error is equal to 0. It eliminates the steady state error. But the proportional controller not eliminating the steady state error, it reduces the steady state error. I hope you understand this well. The second important note here is the overshoot in the output. Okay, so to understand the overshoot in hardware, let's assume that we are working on a speed control system, a system that has a motor and we want to control its speed. So if the desired speed is 100 RPM, so when we run our system, the speed of the motor starts from 0 and then goes up, as we see here, and at this point then the speed of the motor is 100 because it is equal to the input, it is equal to the reference, and then it goes up again in this overshoot, at this overshoot, until the speed becomes, for example, 120 RPM, and then it goes down and goes up until at the steady state it will be equal to the reference input. So this is how you understand the control system classes. Okay, now let's try something else. Let's try increasing the value of the gain in the integral controller. Oh, we have a problem here. We have a serious problem here. When you increase the gain of the integral controller, then the overshoot increases. Look at this value here. It is 1.6. So close this, write this one again, simulate. Look at the overshoot here. It is almost 1.2. So when we increase the gain of the integral controller, the overshoot increases, as we see here. So I want to mention that you need to know the relation of the proportional controller gain and the overshoot value. I am not gonna write this equation here, but I explained previously the steady-state error equation and how we can get this equation from the block diagram, and I explained this as an example. But the main purpose of this course is to focus on the hardware and simulation. Okay, so increasing the gain of the integral controller will increase the overshoot. So the question here is there any benefits for increasing the gain of the integral controller? The answer is yes. Look at this value here. Look at this value and see the time. The time is about 1.5 seconds. And this is called the rise time. So take a look also at the peak time. This is the value of the peak time. Peak time means the time when the system goes to the maximum overshoot. It is equal to 2 seconds. So let's close this window and return this value to 1 and run again. What do you see here? This is the maximum overshoot value, and the time here is about 5 seconds. In the previous, it was 2 seconds. The system here becomes slower, so increasing the parameter of the integral controller make the system faster. But unfortunately, it increases also the overshoot, which is not good for the system. So we have here one advantage and one disadvantage. Is there any way to solve this disadvantage when we increase the gain of the integral controller? The answer is yes. This can be solved by adding the proportional controller to the integral controller. So now we are gonna use the proportional controller with the integral controller. To do that, we need to add another summation point here, so let's do that. Okay, so we add gain for the proportional controller here. We need to connect this gain to this summing point as in this picture here. So we need to click here, double click, and remove this, okay, and add another plus here. So remove this wire, connect this to this, and connect this to this. Be careful when you are connecting the controllers. The controller input is the error signal, and the error signal coming from this summing point. Okay, so now let's simulate the project. Click here. Surprise, right? When we added the proportional controller, it eliminated the overshoot in the system. There is no overshoot here. And if you take a look here, you will find that the output is equal to the input. So we got the desired output from this system. Okay, again, so let's remove this wire, run again. See the system, as we can see here, there is overshoot because we removed the proportional controller. Connect it again, run the system, see the output. So I want to ask you, when the system goes to the steady state value, when the output is equal to the input, this may happen at this point, and this point is equal to 7 seconds. Can we enhance the speed of the system, the speed response of the system? Let's try this. Let's try, for example, first removing this and increase the gain to 5. Run. See the simulation. We have overshoot. Close this. Connect the proportional. Run again. Click here. Oh, so you can see that there is no a huge enhancement here. There is an overshoot, and the system goes to the steady state value maybe at 6 seconds or 5 seconds. So there is a trade-off here. We have here a small overshoot, but the system become faster with about 2 seconds. But let's try something else. Let's try, for example, increase this value to 5 and run. So what do you see here? You see now that the steady state output happens at 2 seconds. So we eliminated the overshoot, we totally eliminated the overshoot, and we made the system become much faster. Okay, so now let's increase this value, for example, to 10. Click OK, run the system, simulate. Yeah, there is a small overshoot here. So we have to be careful. We need to choose the proper value that minimize as much as possible the overshoot and increase as much as possible the speed of the system. And this topic is called tuning. So now I hope you understand the advantages and disadvantages of the proportional controller, the advantages and disadvantages of the integral controller, the advantages and disadvantages of the PI controller.